So, welcome again to the new lecture of the course, properties of materials. So, let us just briefly see what we did in the last lecture. So, in the last lecture basically we looked at theoretical shear strength. So, a simple derivation. So, assuming that stress varies as sinusoidal in a sinusoidal manner. So, in this fashion. So, basically stress in the crystal when you move the atom varies like this. So, this is the distance that atom has to go. So, if the atom was, let us say, if we draw 3 atoms. So, atom was sitting here, it has to go to then this position. So, it has to migrate through an intermediate position which is this. So, 0 to 1, it has to migrate through a position, let us say 0 prime. So, this will correspond to 0, this will correspond to 0 prime, and this will correspond to 1. So, stress varies sinusoidally using this expression, and then by equality of shear stress with shear modulus and shear strain, we can find out that the maximum shear stress required to move the atom will be g divided by 2 pi, and this g divided by 2 pi, and g, the magnitude of g in most crystals varies from 20 to metals 150 GPa. So, as a result the value of tau m is also between 3 to 30 GPa, which is a very large stress. So, theoretical strength is extremely large. You would require strength to move atoms of the order of 3 to 30 GPa, but what it basically assumes is that when you have this row of atoms and when you have another row of atoms on top, and when you are sliding them past one another, this whole row moves with respect to this row. So, which means every atom has to break its bond with the neighbor and then go to the new position, re-establish that bond. So, as a result, a lot of energy has to be spent. However, practical values, the experimental values of strength to cause deformation are of the order of few MPa's. So, for example, for pure metals, they vary anywhere from 0.5 to 15 megapascal, or maybe 0.2 to 15 megapascal. So, they are orders of magnitude smaller than the values that you calculate using theoretical shear strength. So, what is the reason behind that? The reason so we are saying theoretical strength is of the order of GPa's, maybe I do not know 1 to 30 GPa. Experimental strength, stress that is required for deformation is few MPa's. So, discrepancy has to have a reason, and this reason is presence of dislocations or defects inside the metals. So, these defects or dislocations make the material much more softer. So, these presence of these defects make the metals softer than when they are perfect. So, obviously, when you have a material which is perfect, which does not have any defects, it has got to be very strong, but that is not the case experimentally, and we saw various values. So, in 1934 was the time when this dislocation theory, dislocation and plastic deformation was explained, the role of dislocation, how dislocations assist in lowering the stress to cause the deformations, which means real crystals are weaker than and have lower stresses for causing plastic deformation or yielding than the strength values which are predicted from theory. So, So, essentially what happens is that, so let us first look at what dislocations are. Okay. So, we have seen that in little detail earlier in another course, structure of materials, but let us just, for the sake of introduction, let us just see what dislocations are. So, basically we are saying dislocations, as we have seen in a perfect crystal. If you take a perfect crystal like this, let us say this is a perfect crystal, and in this perfect crystal let us make a few grids. Okay. Okay, so you have atoms at various positions. So, these are the atoms sitting in a. So, let us say we choose position 1, we go 2 step up. So, position 2, 2 step up, then let us say we go 3 step to the right to position 3, and then we come back by 2 steps to position down, that is to downward position 4. Then again we walk back to position 1 by taking 3 steps to the left. So, essentially if you complete the whole circuit from 1 to 2 to 3 to 4 to 1. So, 1 to 2 to 2 to 3 to 4 to 1, you do not create any extra step. That is perfect crystal. So, you do not have any atom missing or any extra atom or whatever in the whole thing. But let us say if you have a scenario something like this. So, we have okay. So, what we have here is, let us say if I start now at one, let us say at this point. So, we can see that there is an extra row of atom here in a otherwise perfect crystal. So, this is the extra row of atoms, okay, in a otherwise perfect crystal. So, if this is the case, let us say we go from 1 to some position. So, let us say 1 step, 2 step, 3 step, 4 step, we go to position 2, all right, or let us say we start from here. I think it is convenient to do it from here. So, we start from position 1, let us take 1 step, 2 step, 3 step to go to position 2, which is here, and then we take 4 steps to go to position 2, 3. So, this is position 3, and then we again take 3 steps to position 4 to come down. So, we went from 1 to 2 in one plane by taking 3 steps. We took 4 steps to go to right in the same plane to the right to position 3. We come back to position 4, which is same as position 1, which is same as in the plane in position 1. But now when we want to go back to position 2 by taking 4 steps. So, we take 1 step, we take 2 step, we take another step, we have to go to another step here to go to take equal number of steps, which means I have created an extra step, and this is what is the concept of edge dislocation. You insert in an extra plane of atoms, this extra plane of atoms basically causes a step. So, how does it look like? Basically it looks like as if you have a perfect crystal like this, okay. So, this is a perfect crystal, and the perfect crystal will look like this, but if you wanted to create a step out of it, the step will look something like this. So, you have a step here, and there is this little extra step which is created So, basically it looks as if you have, it is when you move it out, but when it is inside it may look like that the crystal is sort of little deformed if you have because you have an extra row of atoms. So, this is called as edge dislocation. Okay. So, when you have this extra row of atoms, then this is called as edge dislocation, and this extra step that we create is called as Burgers vector. So, of course, when you apply stress to it, the stress to it will move this out of the crystal, leading to formation of this step. So, this will happen when you create a step. Okay. After stress is applied to move it out of crystal. All right. This is what will happen. So, this is basically you can say the dislocation. So, if I now define it, this part of crystal is perfect crystal. So, this region will be basically you can say perfect. This region is perfect in terms of at least atomic arrangement. Shape will be slightly different because of deformation in the lattice because of extra row, and this extra row of atoms which is present here, this is the you can say is the extra row of atoms. So, the plane in which dislocation is going to move. So, you can see that this extra row as you apply stress will either move to the right or to the left. Let us say if it moves to the right, then basically you can see that it is going to move. So, the bottom 3 layers are perfect, it is going to move in this plane where it terminates. So, this plane in which it is going to move will be called as slip plane, and the direction in which it will move will be the basically slip direction. So, dislocation line basically is into the slip plane. So, this is your slip plane and this is the dislocation line. So, let us say this is the slip plane and this is the dislocation line. And that is why edge dislocations are represented as either this or that. So, these are basically edge dislocations. So, if it is from the top it will look like this, if it is from the bottom then it will look like this. So, this is the representation for edge dislocations in crystals. So, essentially what will happen is, this is let us say your slip plane, and you have created an extra row of atoms which is like this. Extra let us say half plane of atoms, in 2D it will become plane, extra half plane of atoms, and the Burgers vector would be either in this direction or in this direction. So, this will be Burgers vector, which is that extra step that you need to take, and the dislocation line is this line, which is represented by a vector T. Okay. So, for a dislocation, so and the stress that is applied is this is, so stress I can, so this is stress tau. So, the following characteristics you can see. So, this basically is the dislocation line. So, for a edge dislocation, one can write B is parallel to tau and B is perpendicular to T. Okay. And so, by this token, tau is perpendicular to T. So, Burgers vector is parallel to applied shear stress. Burgers vector moves in the same direction in which, so the extra row of basically the extra step that you create is in the direction of applied stress. the Burgess vector is perpendicular to the dislocation line. So, dislocation line moves in the slip plane, but the movement is along the direction perpendicular to itself. So, B is perpendicular to T, and and if you combine these two, what it means is that the shear stress applied is also perpendicular to the dislocation line. So, these are certain characteristics of the edge dislocation. The screw dislocation, on the other hand, there is another kind of dislocation. So, this is the first type of dislocation, which is edge dislocation. So, we can say this is first is edge dislocation. Now, the second kind of dislocation is basically screw dislocation. So, essentially this is a dislocation which looks something like, let me try to draw it well. So, this is, let us say, little exaggerated, right. So, you create a step here, this is the step on one side. So, this is the step that you create on the front side, this is the step you can create on the back side. So, basically what you have done is you have moved this half of the crystal with respect to this half of the crystal along this. So, this would be the basically you can say the dislocation line passing through the crystal. So, this is perfect crystal, and this is where you have created the dislocation. So, if you start from this point, point 1, you go to point 2 of the crystal, you come to point 3 of the crystal, and then in order to go to, or let us say the easier one would be you come from this point, you take few steps. So, let us say 3 steps here, 3 steps, let us say you go there, you take 10 steps, you go up, you take I don't know about 7 steps, you come here, you take 10 steps, and then you come here, you complete 4 steps, and to come back to this point you have an extra step. This is the extra step, and this is basically the, you can say, the Burgess vector. Okay, and the line that goes through is called as this, the line across which you have division between the perfect and the sheared crystal. So, this is the sheared part of the crystal, and this is the unsheared part of the crystal. So, basically stress is applied in this direction. So, this is stress, and this would be stress here. So, tau would be applied in this fashion. So, this line, when you apply stress, this line will move in this direction. So, basically for a screw dislocation, you can see for a screw dislocation, as you keep applying the stress, the line, dislocation line, this is the dislocation line. So, let us say this is dislocation line T. Okay. So, for a screw dislocation, this is your Burgess vector B. So, tau is parallel to B, B is perpendicular to T, okay, B is parallel to T, I am sorry, B is parallel to T. So, this is T and this is B, both are parallel. So, by this token T is also parallel to B, but dislocation line moves perpendicular to applied stress. So, dislocation line moves perpendicular to applied stress, it will move in this direction. So, when the crystal is completely sheared, so after complete movement, of course, it will look like you have, there is the top of the crystal, and so basically when this line moves here, you will have created the step completely in this direction. This is the step that you create. Step. So, when the dislocation line would have completely moved of the crystal applying the stress, this would have been a situation. So, this is in contrast to what we see in the edge dislocation. In the edge dislocation, the dislocation line, so you can see in the edge dislocation, Burgess vector is parallel to shear stress, but Burgess vector is perpendicular to dislocation line, and as a result dislocation line is perpendicular to shear stress. However, the dislocation line, the movement of dislocation line, so movement of dislocation line is in the direction of stress. Similarly, here the dislocation, now here on the other hand, the dislocation line moves perpendicular to the applied stress. So, these are two fundamental differences between the two kinds of dislocations. So, in reality what happens is that we do not have perfect edge or perfect screw dislocation, what we tend to have a mixed dislocation. Okay. And these mixed dislocations basically are you can say the part of the crystal. So, basically part screw and part edge. So, we will do detailed discussion on this in the next class, and what we have done in this class is basically we have introduced the concept of dislocations, and we have just stated that dislocations are the ones which take part in reducing the amount of stress that is necessary to carry out deformation. We have not gone into mechanisms of this, we will see them little later. And what we have done is we have just taken a brief relook at the dislocations, what a edge dislocation, what a screw dislocation is, and we will discuss this in details in the next lecture. Thank you.